All right, so we're going to talk about matrices today, and I know that you probably have all seen matrices and even used matrices in your life before, and so, the fact that we're going to put some numbers in between some brackets is not really earth-shattering, right? And when we refer to matrices, we talk about their size, and so we'll say, like a 2 by 3 matrix means a matrix with 2 rows and 3 columns. Rows go horizontally and columns go vertically. And I'm not going to spend our class time on this today. This is the video that you can see on YouTube that goes through a lot of this and does some more examples and goes through some of it a little bit more slowly. So if you find that helpful, it's optional, but you might opt to look there. So what I want to talk about is how do we start defining things for matrices? And I want to start with the idea of matrix equality. And I want to motivate it a little bit by just thinking about, in general, what is equality good for? Well, it's really just saying, like, this is what it means to be the same matrix, right? So if I have one matrix and I want to know, is it the same matrix as this other matrix? This definition is going to tell me how to check. And we probably have some ideas already about what should be the case. So let me see if we have some intuition. So if I write down a matrix A, B, C, D, and a matrix E, F, G, H, K, J. Sorry, I forgot how to alphabetize things. Whatever, we're fine. I want to know, are there any values I could plug in that would make these two matrices equal to one another? Like, is there any way these could be the same matrix? All right, I see some folks shaking their heads. Anybody with a no answer want to say why?
Sure, because no matter what you put in, one will be a 2 by 2, and one will be a 2 by 3. And so even if like K and J are 0, those are still values that matter, and so they can never be the same.
Exactly. So like they're different sizes. Like how could a 2 by 3 matrix be the same as a 2 by 2 matrix? So these are not going to be the same because they're different sizes. So already we kind of know that if we want two matrices to be the same, they should be the same size to start with. And that tells us something that we can add to our definition. We can say two M by N matrices, A and B, which means A and B are both M by N matrices. They have the same size. So already we're starting to figure out, like, if we want to define equality, we better have matrices of the same size. All right, here's another question. I'm going to pick on A, B, C, D. And let's do D, C, B, A. Are these the same matrix? I see some more people shaking their heads. Anyone with a no answer want to tell me why these aren't the same matrix?
Because the order of the variables is different.
Yeah, because the order is different. I mean, if I plugged in like zeros for all of them, sure, they'd be the same. But if A, B, C, and D are all different, then these values are kind of like in the wrong places for these to be the same matrix, right? So, they have mixed up entries. The entries are in the wrong order. So I guess good professor psychology bet is that I should now write down two matrices that are the same. So let's see how we feel about this. Let's do 1, 2, 3, 4, and 0 plus 1, 1 plus 1, 2 plus 1, and 3 plus 1. Are these the same matrix? I already told you they were going to be because I was like, professor psychology says they should be. Why are they the same? Other than I just told you they were going to be.
When you add up the values in the second one, it equals the first.
Yeah, like position by position, they have exactly the same values. I've written them in weird ways. Like I wrote 1 as 0 plus 1, but that doesn't change its value, right? The value over here, 1 and 1 match up in the 1, 1 position. And 2 and 1 plus 1 match up in the 2, 1 position, or the 1, 2 position. Sorry, I got those backwards. But position by position, as we go through and we check, we're like, yep, same value, same value, same value, same value. And that's what our definition of matrix equality is going to be. So two m by n matrices A and B are equal if, oops, let me not write this in the highlighter. The ijth entry of A is equal to the ijth entry of B for all I between 1 and m and j between 1 and n. So it's saying entry by entry, they've got the same values. This was surprising to me when I first started learning more abstract math, that definitions are things that we make up and agree on, as opposed to things that are just out there that we discover. I mean, maybe that's not that surprising to you, but I was like, I just thought like matrix equality was like this thing that existed and we just wrote down the name for it. But actually the way math is done is we're like, okay, we want to do stuff with matrices. What's the most useful way to define matrix equality? And it turns out this is a pretty good way to define matrix equality, right? Like it kind of makes sense that it would. But this becomes important when we start defining things like matrix multiplication. As we'll see on Friday, it's a pretty weird definition, but it makes sense based on what we want to do when we multiply matrices. So it's useful to keep in mind that math is like a human construct that we make in order to solve different kinds of problems. Okay, so then we can add matrices. We can add them by just adding up, you know, entry by entry in the same positions, adding things up. So that's not so surprising. It's like how you add vectors, right? You add vectors by adding up things in the same position. And once we have these two definitions, we can start proving stuff with these two definitions. So let me point out how this proposition and the proof fit together, similar to what I did earlier when we were talking about the first writing assignment. So this proposition says for all matrices A, for all m by n matrices A, which already lets me know the first line of my proof is going to be let A be an m by n matrix. So those match up. And it's saying if I look at this m by n matrix Z, where each entry is 0, something's going to happen. So if Z is the matrix with all zeros, I know that the next line in my proof is going to be assume Z is this matrix that I want to work with. Every entry is 0. And I know what I'm aiming for. I'm aiming for this then statement that says A plus Z is Z plus A is A. And so that's this line down here. A plus Z is A, and we'll see similarly Z plus A is A. We're going to do kind of the same math for both, so we don't need to do it twice. So what I need to do is, for the first part of this proposition, is fill in the math. And the math in this case are those two definitions that we have, matrix equality and matrix addition. So the last line is going to be true because we're going to show that entry by entry, A plus Z has the same entries as A. And so that's where we need to get. So I'm going to start with the definition of matrix addition. By the definition of matrix addition, the ijth entry of A plus Z is the ijth entry of A plus the ijth entry of Z. And Z, it's really easy to write down the ijth entry because it's 0. All the entries are 0. And if I take Aij and add 0 to it, I get Aij. And that is for all I between 1 and m, and j between 1 and n. And hey, that's what the definition of matrix equality is. It says A plus Z has the same entries as the matrix A. So therefore, and I might edit this, by the definition of matrix equality, A plus Z is the same matrix as A. And if we did the same thing with Z plus A, we just have 0 on the other side, and that's fine. We'll just say similarly, Z plus A is A. So that's pretty nice, right? We figured out like the math that we needed to go from what we were assuming to what we were proving. And this proposition is a little bit extra. It has a furthermore, which we'll take care of on the next page. But I see what looks like people still writing, so I won't flip to the next page yet. Instead, I'll just observe that the highlighter colors I've chosen remind me of that summer sherbet that you get that's just 3 different colors. And you can't actually ask like for a flavor. You're like, just give me some of the orange stuff or give me some of the pink. or like whatever that green is supposed to be. Just give me like a little bit of the green. So I don't know, it's like the last gasp of summer here.
May I ask, so this proof is showing the properties of a zero matrix?
Yes.
Okay.
Yeah, and so that's actually, it's a really good question, Sarah, or a really good observation. When I say this is the zero matrix, there are two ways to interpret it. I can interpret it as a matrix that has a bunch of zeros in it, which is fine. But the way that I want to interpret it is it's the thing that acts like a zero for matrix addition. It's like the matrix I add to another matrix that doesn't change it, right? So I could think of, thank you, Sophie. I could think of the number 0 as the number I add to another number that doesn't change the other number. And I can think of the 0 matrix as the matrix I add to the matrix A that doesn't change the matrix A. And so that's like it's like an algebraic property of the operation. So that's how, it's, we'll see this like comes up. We'll have a 0 vector, we'll have, you know, a 0 polynomial, we'll have all sorts of like things that are a 0 thing. And it refers to it like something with an operation, an addition operation. All right, so let's take care of this furthermore. So furthermore is saying that the Z is the only matrix with this property. If I have another matrix that I can add to any other matrix A and get A back, it should be the matrix of all zeros. And the way that I prove this is by assuming I have some other matrix with that property and showing it's the same thing as Z. So let's do that on the next page here. So the next line is, next we show Z is unique. This is just letting the reader know, like, okay, we're getting into this furthermore statement in our proposition. So I'm going to suppose that I have a matrix W that has this property that says, like, whenever I add it to an m by n matrix A, I get A back. Okay, well, cool. Z is an m by n matrix. So let's add W to Z, and we get Z back. Then if I take Z and add it to W, which is an m by n matrix, Z has the property that we get W back, right? We know we add Z to W, and we're going to get the matrix W. And that's it. Now we've got that Z plus W is Z, and we've got Z plus W is W, so they're the same thing. We could do it just like we did on the first page and go through like by the definition of matrix addition and by the definition of matrix equality. But what's cool here is in a proof, we can use something we already showed earlier in the proof to speed things up. So to sort of simplify the logic / writing of the proof. Uh-oh, things are crashing. Oh, thanks. Thanks, Sophie. She's like, it's time to play. Why are you still here? And so that's a proof. That's the end of the proof, and we see our little end of proof symbol here announcing that we finished what we set out to do. There's a little bit more in here, and I'll let you take a look at it. There's scalar multiplication. You can multiply a matrix by a real number, and that just says multiply all the entries by a real number. And the big idea is the idea of a linear combination, which is how we put together matrices using, so it's going to be a sum of scalar multiples of matrices of the same size. Right, so I could take, you know, 3 different 2x2 matrices, scale each of them by a different real number, and then add all of them up and I get a new matrix. And I would say I took a linear combination of my first 3 matrices. And that's going to be one of the things we talk about on Friday when we tie matrix multiplication to the idea of a linear combination of something. And it's what makes all of linear algebra kind of nice. It says when I've got a problem that I need to solve that involves a matrix, somehow, some way I can find the relevant matrix and then just row reduce it and get an answer if I know how to interpret it. So it's like the theoretical underpinning of the idea of matrix multiplication and linear combinations and how they're connected that give us basically like the algorithm, the same algorithm that we do over and over to solve problems in linear algebra. So we're going to talk about it on Friday. Its acronym is the MVP, but it's also actually the MVP, the most valuable player in linear algebra. We're going to use this theorem a lot throughout the semester. So I will stop recording here.